This is a Math 3 lesson summary video for the lesson titled Fred's Flare Formula. This is a develop understanding task. The purpose of this lesson is for students to use simulation to understand how samples can be used to estimate a population mean and determine the margin of error. In this lesson, students look at a situation where the company Fred's Flares makes flares that used to burn for 100 minutes on average, but Fred has developed a new chemical process that should allow the flares to now burn slightly over 120 minutes. And he wants to make the claim on his packages that says now burns for over 2 hours on average. To make sure that that claim is accurate, he wants to pull samples and test the flares to make sure that they are going to be lasting long enough. So he can't check all of the flares because when you use a flare, it is no longer usable and he needs to have flares to sell. So he decides that he's going to take 24 samples. So he's going to pull samples every hour for a day, and each one of those samples is going to have 20 flares in it. So he makes a lot of flares. Every hour he is going to take 20 of those flares and test to see how long they are actually going to burn. So what this dot plot represents, each dot represents a sample. So this dot right here is the average burn time of 20 flares. So each dot represents 20 flares, the average burn time of 20 flares. So 120 minutes was the goal. That's right here. And if you look at the 5-number summary, this 120 ends up right at the first quartile. And that means that you have roughly 75% of the flares that are actually getting 120 or more. And that means you have roughly 25% that are not. So then in the lesson, we look at 24 sample means of a sample size where n is equal to 100. So what has happened here is Fred changed what he was doing. And this is from the same population as before. So instead of every hour taking out 20 flares and finding the average burn time, every hour he decides to take out 100 flares and burn all of those and take the average burn time. So what we can see here is that when the sample size increased, the range decreased. So the larger samples lead to less variability. Now the reason that happens is if you think about if you test 20 flares and take that average versus testing 100 flares and taking that average, if you had an outlier, then the outlier's effect would not be as noticeable in a larger sample. So variability is going to decrease, so the range will decrease when the sample size increases. So then Fred continues to examine the effect of sample size, and we have a couple histograms here. So the histograms represent two sampling simulations from the same flare population, so we're still looking at the same context. In this first simulation, there are 720 samples, so for 30 days every hour. This is simulating for 30 days every hour, taking out 20 flares at a time and finding those averages. And then this other histogram represents having a sample size of 100 flares. So every hour for 30 days, taking out 100 flares. And we can see the same thing happened. There is less variability. The range is smaller when the sample size has increased. So the purpose of this, when you're getting the samples and you're getting the sample means, is that you want to use these sample means to estimate the population mean. So the sample is the small group that we are taking out and testing from the population. And the population would be all of the flares in this case. So if you take all of these sample means and you find the average of the averages, then you have a pretty good estimate for the population mean. So for this first case where the sample size was 20 and there were 24 sample means, the average was 120.46. When we increased the sample size to 100, the average of the samples was 120.49, so still in the center. And then when the sample size was 20 and there were 720 hourly sample means, then the average of the samples was 120.5 minutes. And the same for when the sample size was increased by 100. So you want to estimate the population mean by finding the average of all the sample averages, and that gives you a good estimate for the population mean. So Fred's average was 120.5 minutes, which would mean that he could correctly claim that on average his flares burn more than 120 minutes. So the next thing to consider here is margin of error. The margin of error is loosely defined as the largest expected size of the difference between an estimate and the actual population value that's being estimated. So what that means is it's how much we expect the population mean to vary from our sample mean. The example that it gives here, it has an example where the sample average weight is 45 pounds and the margin of error is 2 pounds. What you do with the margin of error is you add it to the sample mean and you subtract it from the sample mean. And now we have this window. And we can be very confident the actual population mean weight would be between this 43 and 47. So margin of error is the largest expected size of the difference between the estimate, that would have been this sample mean, and the actual population value that is being estimated. Now, to calculate margin of error informally, you can take the range and divide by 2. You may also see this formula, which is the standard deviation divided by the square root of the sample size. But the purpose of studying margin of error in this course is not to be able to calculate it, it's to be able to understand what it is. To understand that it is the most that a value of a sample statistic, like a sample average, is likely to differ from the actual value of the population parameter, the population average. I do think that it is important to look at the structure of this equation for margin of error and also to think about how the sample size and margin of error are related. So if you think about if you increase the sample size, so you're increasing the sample size, and in other words, you are testing more of the population, then your margin of error is going to get smaller because you have a larger sample. The more of the actual population you're testing, the closer you can actually get to knowing the population parameter, that population average. But that should also make sense by just looking at the structure of this equation. This is a fraction. And in a fraction, if you increase the number that's in the denominator, then the value of the whole thing would get smaller. So in a fraction, if you increase what's in the denominator, in this case the sample size, then the margin of error will get smaller. All right, that's it for this video. Thank you for watching.